Hi, everyone. Welcome to Foundry Fireside. My name is Eric, and I'm an intern on the Foundry communications team. And I'm here today for a conversation with Raphael Moral, a postdoc that works with the Foundry's Carolyn Sutter Fellow. Dr. Moral's research focuses on semiconductors that have applications in lighting and energy conversion. Dr. Moral, could you please introduce yourself and tell us a little bit about your research?
Hi, Eric. Thanks a lot for the introduction. Thanks for the opportunity of share a little bit of my research. My name is Raphael. I am a postdoc at the Molecular Foundry, and I'm a chemist, and I work with material science, and I'm happy to be here and talk a little bit about my research.
So, can you give us a description of the project that you're currently working on at the Foundry?
Yeah, sure. I'm currently working with perovskite semiconductors. This is an umbrella term. More specifically, is 2D chiral perovskite. And we focus at the Foundry, and also I normally use the ALS facility. And we focus on the fundamental understanding of the physical chemical properties of these materials, especially during processing of these materials. For example, a film formation, because these films, for example, they can be used in devices later. So we want to understand the intricacies of their formation and their crystalline structures and so on.
Can you define semiconductors in simple terms and explain why it's so important for people to learn about them?
Yeah. So semiconductors are materials that they present the properties between of a conductor, which can be a metal, and an insulator, which can be rubber, for example. And in so that means, like as the name suggests, semiconductors they can conduct electrical current, but they need like a special push for that. So electrons in a semiconductor can be seen as a pinball machine, for example. So the pin, when you pull, represents some external factor that excites the electron to what we call the conduction band. And the electron is the ball in the pinball machine. So an external factor excites these electrons, so pushes the ball up into the pinball machine. And then this electron, when it comes down to its fundamental state, or the ball in the pinball machine, when it comes down, you have then the products that you can extract from this extra energy that the electrons have. In the case of a pinball machine, you have the points that you gain and all the lights that shine up in the pinball machine. In the case of electrons in a semiconductor, you can extract, for example, electrical current or light. So, for example, in your phone, when you take a picture and that light flashes, it's a semiconductor that is flashing light. And then the battery of your phone is this external pin that pushes the electrons to the conduction band. And then when the electrons come back to their fundamental states, they emit the light that we see. So and semiconductors are everywhere. So that's why they're so important.
So, specifically, what is a perovskite?
A perovskite is a natural occurring mineral. So it was found long ago for mineralogists. So it's a mineral where the atoms inside this mineral they have a particular organization. So they organize in a particular crystalline structure. Um, More recently, the metal halide perovskites, which is the type of material that I work with, they are human-made materials, so they are artificial materials that they share the same crystalline structure of the natural perovskites. And this crystalline structure is what makes the perovskites um, have their like special properties, physical properties, electrical or optical, that are useful for us to use in devices.
So why has your team chosen to use these perovskites as opposed to a different semiconductor for your research?
So perovskites, metal halide perovskites, the artificial type, they have attracted a lot of attention from the material science community because in 2009, scientists discovered that we could use these materials to convert solar energy into electricity. And alongside with the solar energy field, all other materials appeared from these perovskites. We can say like derived materials appeared from these perovskites. And the 2D perovskites are a type of this other materials that appeared. And these 2D perovskites, they are very versatile. We can fine tune their properties by changing their chemical composition, and we can change their chemical composition in a endless uh, fashion. We literally have a lot of options to change and tune their chemical and physical properties, and that's why we are so interested in these materials, because we have this huge unexplored field to explore and discover interesting properties, new materials, or in the end, apply these materials to devices such as LEDs. And nowadays, we are more and more interested in the chiroperovskite, so we can also control, as I said before, electrical current, but also the spin of these electrons. And that's why we are excited about these materials, because they're great. They are very they present a lot of amazing characteristics, and they challenge us. They challenge our knowledge. So that's also something that pushes us to keep going.
So what is it that makes you so excited about this research?
The versatility of these materials and the possibility of study these materials from their synthesis in the lab, like mixing chemicals in the lab, so we have the material until their application. So I remember when I first had a collaboration with another friend of mine that is also a researcher. He produced LEDs with materials that I synthesized in the lab. And when I saw the LEDs working in a lab scale, it was amazing for me to see the whole process from the chemical synthesis until the real life, the real world application. And that's what pushes me to keep with this research.
What does your work at the Foundry actually look like day to day?
The work is very diverse. Every day is different. So I I basically work 30% in the lab, 30% in the computer, writing proposals, writing papers, writing presentations for Congress. And also, we here at the Foundry, it's a user facility, so many other researchers come to use our equipment and our unique capabilities. So we also offer support for users in general. So it's a very dynamic and very interesting working environment, very stimulating working environment.
So your team uses X-ray diffraction in your research. Could you define X-ray diffraction in simple terms and explain the techniques that you use and why you use X-ray diffraction?
Yeah, X-ray diffraction is a technique that allows us to basically see how that crystalline structure that I mentioned earlier is. So basically, we can understand how the atoms organize within a crystalline structure in the material. And by seeing how the X-rays interact with this material, so we use X-rays from the synchrotron, for example, we can have an understanding of the crystalline structure of this material. And that's why it's so important, because when we know the crystalline structure of the material, when we know how every atom in the crystalline structure is, where their positions are, we can then understand their properties and further develop the materials and further propose new materials, for example. So this is a very fundamental technique for material science in general.
Wow. So your team uses in situ characterization. Can you define in situ characterization and explain why you use it as opposed to other characterization methods?
Yes. For example, if I am to make an experiment, an X-ray experiment in a benchtop machine, it'll take me about 30 minutes for me to have a single, we call it diffractogram, and then it's just like taking X-rays from your bones, right? Like you can see your bones, you can see the structure if there is anything, broken. So we read the diffractogram in order to understand the crystalline structure. But then in a common machine, it takes 30 minutes or so for a single diffractogram. If we go to the synchrotron, which is a very powerful light source, a single diffractogram can take only milliseconds, for example. And therefore, we can see the material as it forms. So our team, we are specialized in fabricating thin films in situ, meaning that in place, right? We can roughly translate in situ as in place as the phenomenon occurs. So we fabricate the film in one of these powerful X-ray sources, and then because it's so fast, we can see over time how the material evolves from its precursor solution, for example, from its precursor materials until it forms the actual semiconductor that we are looking for. I like to quote a saying that my supervisor says, Caroline says. She says something like, when you synthesize, when you prepare a material, you make like a solution, for example, and then you deposit the solution on a substrate, and you have the material formation. But in between the solution deposition and the material formation, you have a black box that sometimes it's hard for you to understand what occurs inside this box. So in situ experiments is like removing this black box and allowing us to see the intricacies of material formation and their properties.
How did you get into this area of research?
Okay, yeah. During my undergrad, I was always fascinated by synthesis. I always liked synthesis, chemical synthesis. But during my undergrad, I didn't have a strong background on material science, so on semiconductors or solid state chemistry, for example. And then during grad school, I chose to migrate to semiconductors, to solid state chemistry. So I changed my university. I went to a university that was like stronger in this field. And when I started my master's degree, I started working with perovskite nanocrystals, which are very like tiny crystals. And then I just loved it. And because I started working with this particular type of nanocrystals, semiconductors, then I just kept going and ended up working with several types of semiconductors and several type of perovskites, and that's how I'm here. And I still, of course, I still combine my synthesis passion with the material science that I acquired during grad school.
So, what is the end goal or the hope of this research?
Um, so the end goal is always to produce some real world solutions in terms of devices that use a semiconductor. So, for example, solar cells, which is the main, I think it was the main driving force for perovskites in general. But nowadays, there are like a lot of possibilities. So the chiral perovskites, with the chiral perovskites that I work, the 2D chiral perovskite, they have a very special type of property. Not only we can control um, the electrical current coming out of these semiconductors, but we can also control a intrinsic property of these electrons that we call it spin. And because we have this different, like this higher level of control, the possibilities of applying these materials are also increase a lot. So, for example, we can use these materials for quantum computing because we can apply these materials for more efficient processing, information storage, and therefore, in the very long run, for example, if we have more efficient computers, we have less energy consumption, or we have less water consumption if we want to refrigerate those processing units. So yeah, that's why this research is important. But of course, a lot of research and effort has to be done before it's a reality.
So you sort of already touched up on this in your previous answer, but could you just dive a little bit deeper into how the end result of this project could positively affect the environment?
Yeah, sure. For example, as I mentioned before, this supercomputing possibility that we can explore, it's very important for energy reduction, like energy consumption reduction, and also water consumption reduction. For example, nowadays, I guess a lot of people, everyone basically that has access to a computer, is using artificial intelligence, and for that we need large facilities with large processing capabilities, and these large facilities, they consume a lot of energy, and they also consume a lot of water because we have to cool down this processing units. Therefore, if we are able to make more efficient computers, more efficient processing units, we will reduce energy consumption, and we also reduce water consumption because they'll be more efficient and require less water for them to cool down, for example. So this has actually a huge impact in the environment. And as I said before, of course, it's it has a lot of challenges. A lot of effort has to be done in order for us to have this in real life.
Okay, so my final question is, what is the next step that you're going to take in your project?
The next steps include exploration of new materials. As I said, these materials we could we literally have a library of molecules that we could choose um, to synthesize new materials. And although we can hypothesize, we never know what properties these materials may present. They might be super exciting, and then we find like a new material that can be, stable and can be applied to LEDs, for example, or photodetectors, and that's the next step. We are looking into new materials. We are looking into improving the materials that are already reported, and that's why we want to understand their formation characteristics, their crystalline structure, their optical characteristic. We want to understand them better so we can develop further the field and contribute to science and the world in general.
Wow, your work is all really fascinating, and I cannot wait to see what else it leads to. Thank you so much for having this conversation with me today.
Thank you a lot for this opportunity. And yes, thanks for listening.
For everyone watching, thank you for tuning in, and remember to stay tuned for more Foundry Fireside.